thank you so much for doing everything that you're doing we're all learning, and I appreciate you very much. So today's lesson is kind of a hybrid. So check this out. Um, some of you are a little confused about these kinds of images, so I want to make sure you understand what you have here. What you have here is I have 6 daughters and they all wear the same thing and they're all, could you imagine the birth that day? Oh my gosh. Amazing. No, no. Right. You guys saw this video. She moved across the street, right? So let's try this one out. I'm going to get out of the way here. Is this an example of constant velocity? Claim, evidence, reasoning. Is this an example of constant velocity? All right. What do you guys think? So let's think about what constant velocity means. Well, first of all, what's the difference between constant velocity and constant speed? Yeah, direction. You're right. Okay, so is she moving in the same direction the whole time? Claim, is she moving in the same direction? Yes. Evidence. Each picture of hers is lined up perfectly in a straight line. She's the same size in the picture the whole time. If so, it looks like she's moving at a constant direction. Okay, that's one down. What about constant speed? All right, claim. She's moving with constant speed. Evidence. Something that, well, let's go with reasoning. Something that's moving at a constant speed when we take a picture every 10 frames or so. That's what this was. Every 10 frames. Boom, 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 boom. What does constant speed tell us? Constant speed says that we're going to cover the same distance in the same amount of time. Is she doing that? You could argue both ways here. But for the most part, did she have a constant velocity based on this? First, we already said that she has constant direction and she has constant speed because the spacing of the handlebar here is pretty much the same. Pay attention just to the scooter. It looks like we're going a pretty decent constant pace all the way across. Within reason, it looks like it's pretty constant. You could argue that it's not, I'm sure, if you go down and measure with pixel by pixel. But the idea is, can you get a sense that this is constant pace? So our claim is, yes, it's constant velocity. Evidence. The pictures are taken every 10 frames, and so given that they're also moving the same distance roughly the whole time, then therefore that satisfies constant velocity. Constant velocity says that we're going to change our position the same amount in the same direction every single time. Claim, evidence, reasoning, boom. So let's take a look at this. This is our wonderful perusal. You guys are going to take a look through this again and decide what conditions are required to allow for constant velocity. All right. So we have to figure out what the heck a condition is in the first place. Those were the red questions that I had for you on here. Remember, I posted that at the very, very beginning. There it is. You guys answered the green questions already, and now you're going to work on this red question, but you got to read everyone and kind of look at it like, which claims agree with each other, and do you agree with their claim, that kind of stuff. Okay, so we're going to do that. So first of all, one thing I want you to make sure you understand is that this is not, 20 hover pucks. All right, this is one cart. This is one cart. This is one ball. This is one hover puck. Okay. And what's happening is we've taken its picture several times and overlaid it. Okay. So this hover puck here, is it moving with constant velocity? All right. Let's read what some of you had to say. I would have to say that the hover puck is going at a constant speed. I know this because all of the pucks are in a straight line and had equal spacing between them. When objects are placed equally and in a straight line, it means that it's going at a constant speed. Pretty cool. All right. And she agrees with a lot of other answers. So there you go. You see the claim. It's moving at a constant speed, actually constant velocity. And the evidence. The pictures are spaced out evenly. The reasoning. Constant velocity means you're going a constant change in position every single time. And there you go, right? Picture shows that. All right. You can't just say the picture shows it. You have to say, what about the picture shows it? Okay. That's you said the picture shows it. That's evidence. Okay. Why does the picture show it? Okay. Picture doesn't tell you constant velocity. You tell it constant velocity. But what you're telling now, next question: do you have a claim to tell me which way this is going? All right, so let's take a look at this one here. Again, it's kind of hard to focus on the cars because they're overlapping, but there's something that doesn't overlap, and a lot of you picked out that blue little guy on the top. Take a look at that blue guy. Is this moving with constant velocity? Okay, that's your claim. Now, why? What about the picture is telling you that it's moving at a constant velocity? And then why is that telling you that it's constant velocity? So what about the picture is telling you constant velocity? The spacing. Very good. Okay. Why is the spacing important? Right. Constant velocity means that the amount of space in between equal amounts of time is going to be the same and in the same direction. Do we know which way it's going, left or right? No. Do we need to know? No. All right. What about this one down here? Is this moving with a constant velocity the whole time? All right. That's your claim. Now, what's your evidence from the picture? Directly from the picture, what is the evidence that this is moving or not moving with a constant velocity? Okay. What's your reasoning? Remember, constant velocity, the reasoning is basically the physics. What's the physics, right? What the physics is going on here, right? The physics tells us that constant velocity means that we're going to move with the same amount of position change every unit of time. Do we have that here? Okay, that's our reasoning. Reasoning is we use the definition of velocity to help us show how the evidence and our claim supports our claim. Okay, the cyclist and the runner. The cyclist and the runner, you claimed that they are moving at constant velocity. Okay, but you guys even went further and said, hey, the bicyclist is moving faster. Notice where the bicyclist is at the beginning, all the way on the right. And where the runner is ahead. So is the runner faster? We can't use one image to tell whether something's faster or slower. Just because something's ahead of something else doesn't mean it's faster. They had a head start. But let's look at where the bicyclist ends up. The bicyclist ends up here. The runner is back here. Now the bicyclist is in front of the runner. Yeah, that was really cool. Those of you just noticed if something's moving faster, they're going to cover more distance. That's your reasoning. All right. Last but not least, the egg drop. A lot of you had some issues about this one. Some of you said it was constant. Some of you said it wasn't. So let's put this to rest right now. Let's first ask you, if something is moving really fast when you're trying to photograph it, if something's moving really fast, what happens to a picture of it? Yep, gets blurry. So if something is moving fast, it'll be blurry. If it's moving slow, it won't be blurry. It'll be very clear. Right? Notice very carefully that up here, very clear. Down here, more blurry. Right? And the blur is not because of camera angle or anything like that. The blur is actually in the direction of motion. Think about it this way. If I had a bowling ball. Ooh, I do have a bowling ball. Hang on. Told you I had a bowling ball. Whew. Okay, if it was right above my foot, I could drop it maybe 2 inches off my foot. I'd drop it and be like, ooh, that hurt just a little bit. Okay, but if I held it way up here, okay, if this was going at a constant pace, trying to get an idea, if we put it right here and let it fall on my foot, okay, right, that would hurt. Why? It's moving faster when it hits my foot. Okay. Okay, so when we drop stuff, yeah, it's going to speed up. So there's your physics. But let's go look back at this again. If we didn't know that, if we drop this, we're looking at it's blurry here, not blurry up there. It's moving faster. Okay, so it's getting faster and faster. Also, look at the spacing. If we were to imagine that we were to copy this pacing out, sure, the box would get bigger as it comes closer to us. It does a little bit. But the idea is that it seems like even even with perspective issues, it seems like those boxes are getting farther and farther apart from each other. Okay, so that's super important that we see that is the case. Okay, very cool. Yeah, so we have, it is going in the same direction, but it's not going the same speed. All right, so my question for you then is, based on all your observations here, what was different between the ones that have constant velocity and the ones that don't have constant velocity? What's the difference? Let's look back at the previous page. There's two examples right there in the middle. Okay, what was the main difference between here and here? What are the conditions to have constant velocity or not have constant velocity? What's the difference between these two situations? Right? Okay. All right, guys. So now I have a mallet. I have a mallet. I have a mallet. So what we're going to do here is I'm going to take Walt here, my bowling ball, and this mallet to help get this to mimic what we see in our device. So we have a worksheet to fill out. It says start with a stationary bowling ball, then speed up the bowling ball from rest. When I hit this bowling ball with this, what's going to happen? So let's go to the lab, figure it out. Great. Our first experiment is we're going to speed up the bowling ball from rest. With the mallet, we're going to use the mallet to tap on the bowling ball. Watch what happens. Now we're going to roll the bowling ball and then use the mallet to slow it down by tapping on it. See what happens. Now we're going to see if we can get this bowling ball to move at a constant pace with the mallet. What do you think we have to do? When it reaches this point here, we're going to try to see if we can make it turn. So you're going to be drawing this left to right, as you can see, right? Left to right. And when it gets to this point, I want to make it turn 90 degrees. How do we do that? Okay, here we go. Let's say I want to make it turn that way. I'm going to try to tap it just right down this line here. Okay, it didn't turn. Okay, hit it harder. All right, try again. Okay, it still did not turn. It turned, but it didn't turn 90. Okay, that's if I tried to hit it this way. Wait, in order to stop it moving this way, I need to hit it that way. Okay? So let's try this. Coming towards me, I need to stop it. Hey! I made it turn. But I had to stop it first. Okay, try this again. I had to do it, hit this way first, and then this way. What would the combination be? What about this? Check it. All right, here we go. Oh! So far, we've gotten to see some claim evidence reasoning framework to show that reasoning really means what the physics, and evidence is how are we using that physics to support our claim, right? What from the picture, and our claim is whether it's doing something or not doing something or whatever, right? Like, was it moving at constant velocity, was it not? So now we're like, what are the conditions for that? And hopefully you picked up some by looking at a moving a bowling ball, bringing it to a stop, making it start, that kind of stuff. And how do we keep it moving with a constant velocity? How do we make it turn? All right. So hopefully you have some good drawings, some pictures from our video today. And thank you so much. It's been a great time. And I appreciate you. and we'll see you next time.